Hi, I'm Professor David Farina, and in today's lecture we're going to be discussing the Earth and its moon, in particular lunar surface features. Let's get started. So many of you have probably looked up at the moon with the naked eye and wondered, why are there so many different colors on the surface of the moon? If you've ever taken a look through a pair of binoculars or through a telescope, you'll even see some detail on the surface with things like craters and that noticeable color difference. So why do we have areas that are flat, and why do we have areas that are cratered, and why are there color differences between the two? First off, the large areas that are those flat, darker regions are called maria. Now, maria comes from the root word of marine, where we associate with oceans. And early thought was that these flat regions, these dark regions, were the oceans of the moon. We now know that that is not the case. These mare are actually lava plains that were formed. And there are some other regions that are more cratered. And the mare are not cratered, which maybe we can understand a little more about why that is. However, I want to point out that the far side of the moon, the side that we never see, has far less maria, and it's a much more cratered surface. And this should be an indication about what the formation of craters is from. Well, of course, a crater is formed by an impact. An impact crater formed from an asteroid or meteorite or a comet hitting the moon. And the opposite side of the moon, as we've discussed in previous videos, always faces away from us. And so we're seeing the side of the moon here that is never facing the Earth. It's going to have the most impacts, kind of like the bugs on a windshield. You don't end up generally with bugs splattering on your back windshield. It's mostly on the front windshield. So this is the front of the car, essentially. This is the area where the moon is hit by those objects the most. So when a crater is formed, typically the crater itself is about 10 times bigger than the impactor that created it. And so the meteorite comes in, hits the surface, and explodes. You don't generally find the rock or meteorite at the bottom. It's blasted into smithereens. After it hits the surface, sometimes the pulverized crust can melt, creating a flat surface at the bottom. And we end up with these craters on the moon forming over the last 3.9 or so billion years. There is no atmosphere on the moon to erase these surface features through like wind erosion. There's no water for like a water cycle to erode them in that way. And so anything that has happened in the last 3.9 billion years or so has pretty much remained the same. Now, of these surface features, we have both enormous, very large craters, but we also have very small craters. Micrometeorites hit the moon's surface all the time. And this is because there is no atmosphere. So through these micrometeorite impacts, we break apart rocks into smaller and smaller and smaller particles, eventually creating the lunar regolith, the dust, if you will, of the moon. This is produced by micrometeorite impacts hitting and pulverizing the surface. So from our view here on Earth, we can once again only see one side of the moon, and this is the side that we see. Remember, the tidal coupling of the Earth always faces one side of the moon towards the Earth at all times. And as a result, this is the side that we see. We've got the mare, those dark regions. We've got some bigger craters within them, like Copernicus and Kepler here. We also have the Plato crater and the Tycho crater. These are some of the biggest craters on the surface. The mare, on the other hand, are areas where lava plains have effectively covered in enormous craters that were produced after a lot of these other impacts. So we can discuss the age of an impact. For instance, the Copernicus crater has to be newer, younger than the older mare that it is on top of. This is called relative dating. So we're basically looking at the relative age of one feature of the moon versus the other. And this is one of the ways in which we know how old the moon is. Now, of course, we see the difference in color, but there's also a difference in height. Most of these highland regions are more cratered, and the lowlands are the smooth areas, and that should make sense given that these are lava plains. Lava is a liquid. It flows to the lowest surface, just like water does. It flows downhill. And so we've got an area, the mare, being lower and smoother, and we've got the highlands being higher and cratered. Now, of course, we've traveled to the moon, so we have some pictures of the moon from orbit. And we can start to find that there's these things called sinuous rills, which are, we think, the remains of ancient lava flows. These are like lava tubes that have collapsed, maybe during a bombardment. The Apollo landing site, we've got a lunar rover here in this picture. So here's some of that relative dating. You can see how older craters are partially obliterated due to some of those later impactors and some of those micrometeorite impacts over time, and kind of smooths off the edges of them a little more. And then we've got some sharper, newer craters, and we also even have areas where the lava flows have flooded into another crater. So this is younger than this older crater here. So sometimes and I'm going to have to get rid of my face here for a moment for this one, so give me a second. Sorry about that. Let's try that again. All right, so when a meteorite approaches the surface, it hits with high velocity, it creates an impact, as we saw, explodes out a crater. But sometimes, if we have a very, very big impactor, the slumping effect of the surrounding walls of the crater can actually push up a central peak in the middle of our crater. And so you can actually see this in some of the images of very large craters. Let's see if I can go back to here, and we get some central peaks. There's a central peak there. Here's a central peak. There's a central peak. Kind of an interesting little byproduct of some of the larger impactors. Get myself back here again. Excellent. All right. Thank you. So we can see a lot of these impactors, some of the bigger ones, with even just a small telescope. And out of the impactor is these rays of lighter rock material that were ejected, the ejecta blanket formed by the crater itself. So this is the material that used to be inside the crater, is now ejected and strewn about on the surface around it. And it's even more notable here in those maria where we have the dark background, we get a higher contrast. So we've talked a little bit about heavy bombardment, but this is the time frame. So impactors today and the frequency of them is nowhere near what it was in the early solar system. So if we go back to the early times of the solar system, we had a lot of impactors, 10 to the 6th. This is cratering rate relative to present. So we've got about 1 million times more cratering than current day. And then over time it dropped. Then we have this period of late heavy bombardment. This is likely due to the movement of the planet Jupiter. So Jupiter used to be farther out and it's moved closer. And as that happened, it's thought that this late heavy bombardment took place as a result of Jupiter's gravitational action. Now, when we traveled to the moon, we had some major challenges to overcome. We needed to carry enough fuel to make in-flight corrections. We needed to be able to descend to the surface. We needed to relaunch from the surface and then return back to Earth. And in addition to that, we needed to carry enough food and supplies for 1 week for astronauts on board. So this is a picture here of the Apollo 12 descent to the moon's surface, and I highly encourage you to check out the Apollo landing video with LRO data, Lunar Reconnaissance data. It's up on YouTube. Check it out. So what was the solution? We produced something called the LEM, or LM, and this is the lunar module, and basically all it was a device capable of landing 2 astronauts. They left everything above this point right here on the module. This is the part that was relaunched. They left the legs on the surface to this day. Here's the different things that we looked at various different missions. So we have Apollo 11. Of course, Neil Armstrong was the first person to walk on the moon. Buzz Aldrin was the second person to walk on the moon. And Michael Collins actually ended up staying in the orbiter. Remember, only 2 people went down, but there were 3 people on each mission. The date was July of 1969, and they brought back some samples of lunar rocks, which had been able to be using isotopic radioactive dating. They were able to get a range of age for these rocks in the 3.48 to 3.72 billion year old age. So they landed on the Mare Tranquilitas, the Sea of Tranquility, and they collected 21.7 kilograms of lunar rocks. Now we have had then Apollo 12, and then to 14. Remember Apollo 13, they had a major catastrophe and had to reverse course back to Earth without ever visiting the moon. Apollo 15, 16, and 17. It wasn't until Apollo 17 that we had a geologist travel to the moon. Notice at each of these stages we collected more and more lunar rocks, and we went to various different places on the surface. If you want a little more time with this, I would suggest hitting the pause on the video right now so that you can take a look at this chart. Now that you've paused the video, I'm going to move on. So just a quick little look here at where each of these places were. So we have here Apollo 12, 14, 15, and 16. And as I said, they've collected various different rock types. All of these are igneous type rocks. There were no sedimentary rocks on the moon because there are no sedimentary rock creating processes like wind erosion or like water erosion. And so as a result, all of the rocks are igneous, and there's no metamorphism taking place because there are no plate tectonics here. So we've got vesicular basalt, and vesicular basalt is notable because of all these little gas bubbles in it. We've got breccias. Breccias are formed on the moon by impact cratering. So we break up the rock, notable sharp edges here of rock that are mixed and they're cemented together by lunar regolith. And then we've got some older rocks that show a lot of micrometeorite damage as well. So here's Alan Shepard from Apollo 14 analyzing a moon rock, and this has likely been ejected from some faraway region. So here's just a quick little recap on how the Maria are forming. So we've got molten material that kind of seeps up from below and fills in the craters after they're formed. And we've got a picture of the near side of the moon that we always see, and a picture of the far side of the moon as well. Here's a picture from Apollo 14. Once again, a major ejecta rock, possibly from the formation of the Mare Imbrium, which is beyond the horizon. So this huge rock got chucked from well beyond the horizon of its current location here. And here's just a basic overview of the lunar geologic history. So about 4 billion years ago, right after the formation of the moon, we believe there was a huge impact that formed repeated lava flows and formed most of the Mare on the surface. And then over time, we slowly had other impactors take place that have marked up that surface. So we've got Copernicus and Kepler are much younger than the surrounding background Mare. So thanks for watching the video of the Earth and its moon lunar geology surface features. If you like this video and would like to learn more, please click that like button on this video, subscribe to the channel, and if you'd like to learn about every time I make a video, click that little bell at the bottom and get a notification each time I do. Thanks again, and have a great rest of your day.